Hello everyone, I am Dr. Karthika from Department of Biomedical Engineering, SNS College of Technology, Coimbatore. In July lecture series, we are going to discuss about modeling in virtual reality in medicine. In previous lecture series, we have discussed about virtual reality input and output devices, and in this series, we are going to discuss about the virtual reality modeling. First, we are going to discuss about virtual reality physical modeling part 1. Okay. See here, the virtual reality physical modeling elements. Here the main element is haptic interface control, visuals interfaced with haptic interface in virtual world. And here we have elements like collision detection, grasping, surface deformation, compliance and texture, hard contact and physical constraints. See here, the haptics rendering pipeline. For better understanding, I have taken this haptics rendering pipeline. Here I have traversal, force, tactile and display. In the part 2, we have application, geometry, rasterizer and display. The first thing, in traversal part, we have collision detection. In force part, we have force calculation, force smoothing and force mapping. And in tactile part, we have haptic texturing. And finally, we have display. And in application part, we have scene traversal. While coming into geometry, it includes view transform, lightening and projection. And rasterizer, we have texturing. And finally, we have output display. Okay, first we are going to discuss about traversal collision detection. Okay, what is the necessity of collision detection in virtual reality? Why do we need this collision detection? Okay, see here. Here we have two sizes of bounding box. One is fixed, another one is variable size. Why do we need this fixed and variable size bounding box? Actually, the main motto of virtual reality is to provide a real world experience. Real world objects are, some objects are similar in size, some objects are different in size. So, to map a real world experience with virtual world, we use fixed size or variable size bounding box. Based on the object orientation, we can choose either fixed size or variable size. That's it. Okay, by using bounding box, collision detection for faster response. And here we have two types. One is fixed size, another one is variable size, depending on enclosed object orientation. And fixed size is computationally faster but less in precise. But variable size is computationally slower but it has high precision. Okay. Okay. Next one is about collision detection in world coordinates. Why do we call it as world coordinates? Actually, virtual reality uses world coordinates because it provides real world experience by mapping the real world with virtual world. So we use the coordinates world coordinates. Like for object 1, we have K1, I1 and J1. For object 2, we have K2, I2 and J2. So here the coordinates are IW, JW and KW. For object 1, the pointer is P1 and object 2 is P2. And here we have O1, O2 for object 1 and 2 and OW for world coordinate. Here we have bounding box which size is fixed or variable depending on the real world object. Okay. Next one is, if collision is undetected, what will happen? Consider a ball at time t and ball at time t plus 1 by FPS. What do you mean by this FPS? FPS is frames per scene or frames per second in scene. Okay. Here, if longest distance d is less than v multiplied with 1 by FPS, then collision is undetected. Here v is the ball velocity along its trajectory. Okay, and why do we need this two-stage collision detection? For more precise detection, we use a two-stage collision detection. An approximate bounding box stage followed by a slow but exact collision detection stage. See here bounding box pruning multi-body pairs, and we have pairwise exact collision detection and collision response and simulation. If collision is detected, S pairwise exact collision detection is enabled and collision response followed by simulation. If no means the simulation and provides real world object orientation. Okay, For exact collision detection, we use Voronoi regions. For object A and B, consider this objects A and B, we use external as well as internal Voronoi regions. See external Voronoi region and internal Voronoi region in this figure, and here we can also extract the features of this objects, because we have to map internal as well as external Voronoi regions with its features in virtual world. So we use the concept external, internal Voronoi regions with its features. Okay, and the last one is surface cutting. An extreme case of surface deformation is surface cutting. This happens when the contact force exceeds a given threshold. When cutting, one vertex gets a co-located twin. Subsequently, the twin vertices separate based on spring or dampener laws, and the cut enlarges here. Here, mesh before cut. See, with the help of cutting instrument, we can cut it. Mesh before cut and mesh after cut. See the differences. Okay, here we have collision response, surface deformation, uncut mesh and mesh after cut. The mesh after cut, it provides a perfect real world experience in virtual world. Thank you.